Hello everybody, my name is Brennan Beam and I'm a hydraulic engineer at HEC. In this video I'm going to talk about the calculations in HEC-FIA. We're going to start with the direct damage calculations. On the screen now we're looking at the stage in the river over time. For each structure in the study area we have a depth damage relationship. We're going to look at the maximum water surface elevation at the location of that structure and subtract the first floor elevation of the structure to get the maximum depth. We take that maximum depth and find its damage on the curve. In this case, it's sitting at about 68%. So if we assume our structure has $100 of value, then we assume $68 of damage to that structure. That same basic principle applies to content and vehicles. There's an additional calculation at each structure though. So instead of just looking at depth, we're going to look at depth times velocity. What we're trying to get a gauge here of is even if the depth doesn't reach the maximum damage of the structure, a lower depth with enough velocity could just knock the structure down. So looking at that same structure, we have a threshold for total damage that we assign to each structure. We can look at the maximum depth and velocity times velocity for that structure in that location and rate that against our depth times velocity threshold. And if it surpasses it, like it did in this case, we assume that structure collapses and has 100% damage. Agricultural damages depend on the crop type, the duration of flooding, and the arrival time of the flood. The relationships in the top corner here, you've got the red one and the blue one, are specific to that crop type and duration. So that blue line would represent a long duration of flooding for this particular crop. That red line would be a short duration of flooding. So for any field we have, we can take a look at the hydraulics and get the arrival time of water to that field, and we can plot that arrival time on the function that corresponds with the duration of flooding in that scenario. There's other interesting interactions with agriculture that aren't captured in that pretty simplistic accounting. We have sedimentation as a big one. If you're working with a river that's full of sand, those crop loss functions might not be appropriate because if there's any duration of flooding, that river might be dumping feet of sand onto your fields and no crop is going to survive that. If that happens, not only are those crop loss functions maybe suspicious, but now you have cleanup cost. Got to move all that dirt off, and opportunity cost of not likely being able to replant that season and perhaps not next season, depending on how bad it is, of course. Another interesting interaction, some crops can withstand flooding. Tomatoes are okay to be flooded a little bit. It's not the end of the world for them. But if that floodwater passed through a tobacco field upstream before it flooded those tomatoes, then you have the possibility for tobacco mosaic, which is a flooding transmitted disease for crops. So those types of interactions aren't accounted for in the agricultural compute and are things that you'll have to investigate kind of outside FIA. Okay, the final compute we're going to talk about is life loss. And to understand life loss, I'm going to introduce this warning and evacuation timeline. This timeline is important because it's going to define the amount of time that the population at risk has to evacuate. So starting first with the warning delay time. The warning delay time spans the moment the threat is detected, that there's something going wrong that's going to require an evacuation, and somebody telling everybody they need to evacuate. So in this example, let's pretend that it's a dam breach. So the hazard identification is going to be somebody, probably the dam operator, noticing, hey, there's some really awful seepage. The dam is going to fail. Once he's figured that out, he's got to tell somebody. Whoever's responsible for delivering that message to the public. For this example, let's pretend it's the sheriff. So the sheriff's got to deliver the message to the public. He's going to get that message. He's going to go to whatever system he has to issue the warning and do it. That time span defines the warning and delay time. Next, we're going to be looking at the warning diffusion time. So this spans the sheriff having released that message to the public and people actually getting it. So the things that would impact this are, how many channels do you have to deliver that message? Do you have a reverse 911 system? Is it a calling tree? Is there sirens? Are you having to send the alert through snail mail? What are you working with here to get that message out to the public in a reasonable time? Once that message gets to the public, there's still another delay between somebody receiving the message and somebody actually acting on it. That's the protective action initiation time. And this is going to be based on how good that message is. Does it have the adequate information? Is it persuasive enough? And how connected is your population? Do you have isolated groups that aren't going to get the message? Is the message only in one language? And so the Spanish-speaking population won't be able to understand an English message as easily, might increase that delay time. Factors like that are going to extend this time. Now finally, people have acted on it. There is the evacuation time. And there are two options here. You can evacuate horizontally. That's what we think of when we normally say evacuation. This is people leaving their houses and taking off and getting out of the hazard area. In FIA, there are some assumptions made that other software that HEC provides, like HEC LifeSim, doesn't make. And that is, in FIA, we are going to assume that the population at risk is going to take the shortest distance out. They're going to cut through mountains and buildings and fences. They're just going to dart out of the hazard area. And they're going to travel at whatever speed we set. So there's no evacuation modeling. We're not modeling traffic. So there's a huge assumption you have to put into your model right there. If this is a really important component of your study, it might be worth looking at a model that's better suited to do this kind of analysis, like HEC LifeSim. If the population doesn't decide to evacuate before the water gets to their house, we assume they're going to evacuate vertically. So all population at risk is going to go to the highest story of their building. Population under 65 are going to go up into the attic or the roof if there's access. Once each group is in their safest location, FIA is going to assign them to a fatality zone based on the water level. Water levels less than 4 feet are considered safe, very unlikely to lead to fatality. Between 4 and 6 feet, now the water's covering the mouth and nose of most adults. That group is going to get assigned a more intense fatality rate that we're going to call compromised. Above that, we consider that the chance zone is the high-risk zone, and conditions are much more likely to be lethal. Now, for each evacuating group, FIA is going to sample a random number between 0 and 1. That number corresponds with the probabilities on the x-axis of this chart. The fatality rate is going to be pulled off the curve that corresponds to the hazard zone that group was in. This means, on average, that proportion of the group will perish in the simulation. For example, if a group of 2 in the compromised zone samples 0, which is going to correspond with a 0.5 fatality rate, 1 person will die in that structure. Now, to tie this back together with all the other computations, this hydrograph represents the entire time span of our simulation. So we've got a warning issuance, a non-evacuation depth, and all the time between them represents the evacuation opportunity. So prior to the warning issuance, we have that warning delay time. After the warning is issued, we still have the diffusion and the protective action initiation delays. Now from this, we can also get the maximum depth, which we're going to use for folks who were not able to get out during the evacuation opportunity to categorize into their hazard zone. And that's the end of this presentation. If you have any questions, please feel free to contact me directly or post any of your questions to the discourse discussion board.